So we want to calculate what's g of pp. So of course it is what? It is p naught squared minus p1 squared minus p2 squared minus p3 squared. So generically speaking, that's what? That's, well, that's the energy squared divided by c squared minus what? Minus m sub 0 squared gamma squared v dot v. All right, fine. But can you think of a way to, that is what it is, but this is equal to what? It's the same quantity, what, in rest frame? What does this simplify to? What is the invariant interval in the rest frame? We know that they're equal. If you compare two different frames, it's the same quantity. That's the thing. So in the rest frame, what's the invariant interval? V is equal to 0, right? And the energy, the relativistic energy, is just what in the rest frame? This V is 0. This just simplifies to m naught c squared. That's the famous E equals mc squared. So it's just m naught c squared. So the rest energy is it. The invariant interval of the form momentum is the rest energy. You guys seem wiped. Did you guys have like a hard engineering test earlier or something? Or is it just me? Don't answer that. Let's see here. I could show you the addition of velocities in arbitrary directions and such using this technology, but that seems like it's going to blow up in my face. Let me try something else. Here's one that's an actual problem. Here we go. I think this will help. Problem. Actually, if you understand this problem, you're a long ways towards where you need to be. In this material, a particle of rest mass m, a particle with rest mass m is at rest. There it is, minding its own business, at rest. When it splits into two particles, each of rest mass little m. I'll give the big M feet. There we go. Which move with velocities u 0, 0 and minus u 0, 0. Show that big M is equal to 2 little m times gamma of u. All right, so the principle that I need to share with you is that it's an experimentally determined fact that form momentum is conserved. So like if you're in a frame of reference and you observe some physical process, form momentum will be conserved in that process. There's some interplay between energy and momentum, and it's completely described by form momentum. So I can look at the momentum before, right? And I can look at the momentum after. Which will we do what? I mean, so basically I have the momentum of big M is equal to the momentum of little m plus the momentum of little m. I need, the label is not good. Let's say P1 plus P2, where these are of the little m's, okay? Now, my first move is just to write it down in the, as it's given, right? What do we have? The initial, it's at rest, right? So we've got big M c squared 0, 0, 0 is equal to what? What's the momentum? What's the form momentum, rather, of the masses afterwards? Well, it's little m c squared times gamma of u, comma, let's see here, gamma of u times u 0, 0 plus mc squared gamma of minus u. I mean, I say of u, guys. This u is supposed to be the speed. It just so happens that the vector, let's say u 0, 0 has what? Magnitude of u is what? It's just that again. I mean, so this is the speed. U is assumed to be positive here, all right? So I can, gamma of minus u gamma is an even function, right? It doesn't care whether it's going left or right. It's the same scale factor. So like I could write gamma of minus u here, and I will, but well, fine, I won't. It's gamma of u again, because of the way gamma is the formula for gamma. So again, gamma of u. Now this time what? What am I missing? If my second is for the one that's moving with the velocity to the left. I'm missing a minus, right? There should be a minus in the relativistic momentum. The relativistic momentum of the second little mass is moving in the opposite direction of the first one, let's say. So there's a minus here. So what happens? I mean, you add these, nothing especially interesting happens. These cancel, right? And basically the only interesting information you get is from the 0th component, right? This guy has to be equal to that guy. Oh, and okay, there's also one over here, right? So therefore, m is equal to 2 little m gamma of u. I'm going to tell you the result of another answer and talk about its physical meaning. Elastic collision. If you have a particle of rest mass m, all right, moving with velocity u relative to some inertial coordinate system, all right, and it's moving with velocity u relative to some inertial coordinate system, and it collides elastically with a second particle, also of rest mass m, which is at rest. Oh, I'm sorry, this may be bringing back bad memories for you. Do you guys remember what happens? Oh, it wasn't such a bad memory. I just threw it out. I should have just kept it in there and just killed your scores, but I didn't. I threw it out. Hope you're happy. I died a little bit by doing that. Let's see here. Yeah, so we found 90 degrees, right? And then you laughed at the fact that I thought you might be able to do it. But I do. You could do that problem if you believed in yourself. Power of positive thinking or some such nonsense. Let's see here. Where am I? After the collision, the particles have velocities v and w. Bang. Collided. So afterwards, the one's got velocity v, the other one's got velocity w. All right? And you can measure the angle between them. We proved, well, I proved, that's 90 degrees in terms of classical mechanics, right? You can work it out using this invariant interval business. It's about a page. It would take me, a half hour to work through it carefully with you guys. But it turns out that what you get is cosine theta is equal to c squared, and this is on page 130 of Woodhouse, c squared divided by vw times 1 minus the square root of 1 minus v squared over c squared, parentheses, open parentheses, 1 minus the square root of 1 minus w squared over c squared. Oh, in other words, it's equal to, no, I can't write that nicely. Well, anyway, there it is. That's the relation. So what happens is that if v and w are much, much smaller than c squared, what happens then? What's that? I mean, there's a couple of competing things here, but if you calculate the limit carefully, in the limit that v and w, well, let's say v over c and w over c go to 0. Yeah, this is troubling, isn't it? But basically in that limit, these both go to 1 minus 1. And so if we were to work it out carefully, these win. And we get cosine of theta equals to 0, which is what we found. Right? Or you could look at it this way. If you let c become infinity, see, I don't know, there's still an ambiguity here. Anyway, careful analysis of the limit, which I'm not doing, reveal that cosine of theta equals to 0 in that limit, that the velocity of light is much, much faster than v and w, which is the classical limit, which is the one we already calculated, right? Cosine of theta equals to 0 is 90 degrees. This is actually one of the ways that special relativity has been tested experimentally. We have these things called bubble chambers, all right? And you have very, very energetic particles that are going super, super fast. And when they go through the bubble chamber, they rip electrons off the gas, and they leave a little tick, 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 like that. And so you can see where a particle was at rest, right? And another one hit it, like it's probably an electron, and then they just go like that, and the angle between their tracks is not 90 degrees, despite the fact that those collisions should be elastic. It's something else. And this is further experimental confirmation of special relativity, that you don't have 90 degrees for this kind of elastic collisions with a particle at rest of equal mass. We know that the particles are equal mass because we're like talking about elementary particles. It's not like an electron says to the other electron, I went on a diet. Like, you can't do it. You're an electron, you have a certain mass, you're stuck with it, It's not like I want to be better than all the other electrons. Like, it's just not possible. There's just electrons, right? So, yeah, the whole concept of individuality breaks down in terms of elementary particles. All right, there's a problem in your homework about the Schwarzschild radius. Do you guys know about the Schwarzschild radius? What's a black hole? Well, some dude back in the 17th century said something along the lines of this. If the gravitational attraction of a star was so strong, right, that it made things fall to the star faster than the speed of light, then if you shined a light and you were close to such a star, the light couldn't escape. So it was called the dark star because that was his idea. But then later people gave up on it because they're like, wait a minute, how does gravity act on light? That's hard to understand with Newtonian gravity. But then we found general relativity where, again, gravity does act on light, in fact, and the idea of a black hole makes sense. In fact, Schwarzschild found these spherically symmetric solutions to Einstein's equations in like 1918 or something like that. And then much later, we came to the interpretation of them as black holes. Nowadays, we think there's something called supermassive black holes at like the center of most galaxies, because if you look at the center of galaxies, you see stuff just whipping around. Like there's some stupidly large gravitational attraction at the center of galaxies, and you got like stars just zipping around really, really tight, fast orbits, which says that there's some kind of crazy mass there. And the only way we can understand that is through these things called supermassive black holes. The Schwarzschild radius, and this is something I will not try to derive in here, obviously, is just the simple of the following relation. Schwarzschild radius is equal to 2 gm divided by c squared. So if you want to know what's the Schwarzschild radius, you take the mass that's forming the black hole, you multiply by the big G, that's 6.67 times 10 to the minus 11th, you divide by c squared. A convenient reformulation of this is as follows: 2.95 your mass divided by the mass of the sun, and that gives you kilometers. So for example, if you were to take the mass of the sun, all right, and condense it so far down, right, that it, you could somehow take the mass of the sun and collapse it so far down that it made a black hole. In other words, it's so dense that even light can't escape it. Then your black hole would have a Schwarzschild radius of what? I guess 2.95 kilometers. So, which is kind of small, given the mass of the sun, right? That's like really, really dense. So anyway, the story of black holes is an interesting one, but I will let you read about it and watch about it, and I'll shut up. Next time, I promise, no relativity, just waves.
Dr.
Yep.